In this video I'm going to show you how parametric equations can be used in physics to model projectile motion. So if you ever played a game like Angry Bird where there's some sort of target that you're trying to hit and you have your sort of slingshot and you want to get the Angry Bird to hit it, well, you have two decisions to make. You have to decide how far to pull back the slingshot. That will change the what's called the initial velocity of the projectile. And then you also have to decide what this angle is. And depending on those two things, you may or may not hit the target. Now, when you release it, the bird makes a parabola-like shape, and that has to do with the force of gravity. If there was no gravity, the bird would just go in a straight line. So you have the bird trying to go in a straight line, but you have gravity trying to push it down, and those two motions come together to become the parabolic shape that we're used to seeing. Now, back in Algebra 1, they would have a question like this. If the height of a ball is determined by the equation negative 16t squared plus 112t plus 128, when will the ball be on the ground? And for that question, we're asking, when is the height going to be 0? In this case, we could factor out a negative 16 and get t squared minus 7t minus 8, which factors to t plus 1, t minus 8, which gives us an answer of 8 seconds. Now, if I were to graph that situation, it would look like this, t and h. So after 8 seconds, the projectile's on the ground. But these units here are time. So this actually says nothing about the path of the projectile. This projectile could be going straight up and straight down in 8 seconds. Or it could be going to the left or to the right. It could be going to the right at a wide angle or something like that. We don't know. There's nothing about horizontal displacement in this. That's where we need a parametric equation. So the y equation is the equation of the height, which is negative 16t squared plus. Now, if this is v0 and here's theta, if this is a right triangle of forces here, the vertical displacement is, at least in the beginning, is v0 is the hypotenuse times sine theta. And the horizontal displacement is v0 times cosine theta. So in this equation, this is gravity pulling down on the thing, but it's also trying to go upward, or at least, this is sort of the upward velocity. Those two things are fighting against each other. And there's also our initial height, which might not be on the ground. So I have that. So there's a lot of variables here. The x equation is a lot simpler because the horizontal displacement has nothing to do with the vertical displacement. It actually is constant speed. So I'm going at this speed in the beginning, and I continue to go with that speed. This is like neglecting air resistance and things like that. That's a v0. So those are our two equations. And we can use these to do some scenarios. Like, suppose I know my initial height is 6, and I'm firing this projectile at an angle of 35 degrees with an initial velocity of 88 feet per second. And I want to know where is it going to land. Okay, I just had paused and started again, so I'm not exactly sure where I was, but from what I see here, we have our situation. We want to know where this thing is going to land. And and there are two things. There's when is it going to land, and then how far from the starting position will it land. Our equations are going to be y equals negative 16t squared plus 88 sine 35 degrees times t plus 6. And our x equation is going to be 88 cosine 35 degrees. This whole thing is kind of like the coefficient of the t. Same thing with that. So this projectile is going to go up and down, and where it lands has a lot to do with when it lands. And for when it lands, when it does land, the y value will be 0. So by plugging 0 in for y here, minus 16 t squared, this is this whole thing is about 50.5. This 88 sine 35. And then if you do the quadratic formula, which I'm not going to do out, but I'll just tell you, you would get t equals 3.3. Then you'd also get something negative. That would be like if you went sort of back here, which isn't going to happen. So 3.3 is the amount of time that passes until it lands. You plug that 3.3 in place of the x equation, 88 cosine 35 degrees times 3.3, and you get 236 approximately feet. So that's the answer. So given, in that case, we're given these two things, and we're figuring out this third one. We're also figuring out the 3.3. Okay, scenario number 2. In this one, we are forced, we're told what the angle is, and we're told how far away our target is, and we want to figure out what should V0 be, like how strong of a force should I do that will make it hit that target exactly. So our equations are y equals negative 16t squared plus V0 sine 40 times t. This is plus 0 because this one actually is starting on the ground, and the x is just going to be V0 cosine 40 times t. So what we have is we have a lot of variables here. We have x, y, v0, and t. The trick to this equation is to take the x equation and rewrite it as v0 equals x. Sorry. Let me go back for a second. We know that when it lands, x is going to be 400 because it's given to us. So we can say that 400 equals v0 cosine 40 t. And I have a choice here. I can either isolate the v0 or the t. I'm going to isolate the v0 because there's only one of them in this equation. You'll see when I do substitution. So I get v0 equals 400 over cosine 40 and times t. T's there in the denominator. Now if I take this and substitute it in place of the v0 in the other equation, I am going to give myself some room. And we also know that it lands on the ground. So y is going to be 0 when it hits the ground. So I say 0 equals negative 16 t squared. Instead of v0, I'm going to write 400 over cosine 40 degrees t times sine 40 degrees t plus 0. The t's cancel out. I'll move the 16t squared over. I can calculate out sine 40 over cosine 40, or I could just rewrite it as tan 40. Either way. Sorry. it'll be 400 times tan 40, because it's sine over cosine. And then I can divide both sides by 16 and take the square root of both sides. So I end up with this expression, square root of 400 times tan 40 over 16. That actually does turn into 20 over 4, or 5 tan 40. Sorry, 5 square root of tan 40. Either way, it becomes 4.6 seconds. So 4.6 seconds is how much time passes. The question, though, was what's the initial velocity, what's v0? So if you plug the 4.6 into that t, into that equation, v0 equals 400 over cosine 40 times 4.6, we end up with about 114. So if I'm forced to have a 40-degree angle, and my goal is to make it go 400 feet far, my initial velocity would have to be 114 in order to achieve that. The third scenario is the most complicated of them. In this third scenario, we know our target's 200 feet away, and we're launching it from ground level, and we know what our V0 is. V0 is 100 in this case. And the question is, what should this angle be? It turns out that there's actually two answers to this question, and I'll show you how to find both of those answers. So our equations are x equals 100 cosine theta and y equals negative 16 t squared plus 100 sine theta t plus 0. It starts on ground level. So those are our two equations. Since we know that 200 is how far it goes, I can take this equation and plug 200 in for x. 100 cosine theta, sorry, I forgot the t. 100 cosine theta t, and I could solve for, isolate the t. So I get 200 over 100 cosine theta, which is 2 over cosine theta. Now y, just like before, y is going to become 0 when it's on the ground. So I get negative 16. Instead of t, I'm going to write this 2 over cosine theta squared plus 100 sine theta. Instead of t again, I'll say 2 over cosine theta. And now, pretty ugly equation. If I multiply everything through by cosine squared theta, I get 0 equals negative 64. This becomes 4. Plus, if I multiply, I'm just going to write cosine squared theta on both of these terms because I'm multiplying all the terms by it. Even the 0, but it stays as a 0. This cosine theta cancels out with one of these. I end up with negative 64 plus 100 sine theta, cosine theta, or 64 equals 100 sine theta, cosine theta. That should be 200 because there's a 2 here. Now, it seems like there's way too many variables here, but there's a trig identity that says that 2 sine theta cosine theta is equal to sine 2 theta. That's an identity that comes in handy right now, because if I divide both sides by 100, I get 0.64 equals 2 sine theta cosine theta, which can now be replaced with sine of 2 theta. Now, just like an equation, if I said like sine theta equals 0.64, there'd be two answers. We can say sine 2 theta equals 0.64. The reference angle, we have to do sine inverse of 0.64, and we get 40 degrees. So we can say that 2 theta is either 40 degrees or 2 theta equals 180 minus 40, which is 140 40. You have to look at a Trig video to see why there's like two answers to that question. I don't want to get into that right now in this video. Divide both sides by 2 and get theta equals 20 or theta equals 70. Those two answers will always add up to 90, just like these two are always going to add up to 180. Well, that's the way this question works. That's scenario number 3, and those are all the scenarios.